We'll start the first topic of this course. It's called fluid statics. So as the name suggests, we are going to talk about stationary fluids. So no motion, no movement in the fluid. And as we also discussed earlier, that in fluid mechanics, we need to identify certain variables so that we can completely characterize the flow. So we talked about these fields called the velocity field and the pressure field. So if you know about the velocity and the pressure fields, then you have characterized the flow completely. Of course, fluid properties and so on are known, but in terms of the flow behavior, this is what you need. Temperature is required if you're interested in energy balance. Mostly that comes when you start talking about heat transfer. That's an advanced part of fluid mechanics. So in this course, we'll be interested in these two fields. And when you talk about fluid statics, then even this one goes away because you're talking about stationary situations, that is no velocity. So V is equal to 0. So all we need to know in fluid statics is the pressure field distribution. Okay, so let's take a situation where you have where you have a solid body which is let's say immersed in a fluid. And you would want to find out the force acting on the body because of the pressure of the liquid or the fluid. Okay, that's typically what we do anyways. I mean, the reason we need to know pressure is to calculate the force because of that pressure on some other body. So let's say we have, since the body is arbitrarily shaped, so we'll take a small area, an infinitesimal area on the surface of this black solid body. Let's say the area has an outward normal called n hat. As we know that for areas we use vectors to denote the direction of the outward normal to the area. And this infinitesimal area is denoted by d gamma, capital gamma symbol. This is a solid, let's say. Okay, and the force acting because of pressure of the fluid on this area d gamma, we'll call it as df. That's equal to the pressure acting at that point. So pressure as a function of x, y, and z times the infinitesimal area d gamma. And then, of course, this is a vector. So the direction is always, as we know, in minus n hat direction. So the force always acts opposite to the area. So this is typically what we need the pressure for, that is to calculate force. And in case you want to find out the total force F acting on the solid body because of all the forces, because of the surface forces due to pressure, is simply the integral of dF over the complete area gamma of the solid surface area. Right. So that's quite intuitive anyways. It's just a bit of a mathematics here, but otherwise the ideas are all clear to us. And remember, you'll hear these words, and we'll also talk about it. The forces are, you can split the forces into normal forces, that is the one that I just talked about, this df, and also shear forces. Shear forces in this case will not be there because the fluid is stationary, but for a flowing fluid, if the fluid was, let's say, flowing over the surface, it will apply some sort of friction over the surface, some shearing. So generally you can split the force into normal and shear, that is tangential. And then the normal force is taken care of by pressure. And now again, I'm speaking these things very loosely. When you do a course in continuum mechanics, you'll do it more in a more quantified way in terms of quantities called tensors. And then the shear force is due to shear stress. Okay, and then we'll say that the total stress is a sum of the normal stress and the shear stress. So pressure is what will apply the normal stress. Again, pressure is the isotropic part of normal stress. But again, these things right now we just want to get some intuition out of it. So whenever we talk about fluid statics, we will only be talking about the normal stresses or normal forces or pressure. And when we talk about the moving fluids, starting from next lecture, we'll be talking about shear stresses, because the normal stress or the pressure is not as interesting as shear stress. Okay, but again, a word of caution. Sometimes we get confused about the fact that pressure only exists in stationary fluids. That is not the case. Okay, so pressure also exists in moving fluids. And in fact, you already know that if you have a pipe, you need a pressure difference between A and B. You need a delta P between A and B to generate that flow. So even the moving fluid has a pressure. In fact, the moving fluid at this point will have higher pressure than the moving fluid in across this cross section. So pressure, or we also call it static pressure, instead of pressure. So that is also there in moving fluids. I'll keep highlighting these things as we go on. So I'll keep repeating these things so that they become more of a habit for us in fluid mechanics. But in case if you ever get confused, do feel free to discuss with me, because many books will use different terminologies. So you may get confused, but that's a good thing if you get confused and then you question things and understand from your own perspective. Now, applications. The application of fluid statics, particularly for engineers, is in ships, designing and manufacturing, designing ships, submarines or submersibles. In fact, I sent you a video on submarines this morning. Then more for the civil engineering side is dams and reservoirs. Okay, then we also deal with fluid statics a lot when we are working with pressure measuring instruments. Towards the end of the lecture, we'll talk about these things. So these are sensors for measuring pressure. And that is typically done by mostly by mechanical engineers, but also have a knowledge of other fields such as electrical engineering these days, because most of the sensors are electronics, semiconductor based. Right. So these are the typical applications. So you'll be if you're working with fluid statics, then you most probably will be working with these industries related to these applications. Right. So as I said that all we need to do in fluid statics is to find the pressure field P. And why do we need to do that? Because then that will result in a force on the body. So we'll have to find out the forces on the body. So let's do that. Let's quantify these things. Let's develop some equations that help us relate the pressure field in a situation to the force acting on it. So let's take some fluid. And then in this fluid, what I'll do is I will take a fluid volume. There's no solid body here. In fact, I've taken an imaginary fluid volume here. So imaginary collection of fluid particles, and this is all stationary. There's no movement here. And what I want to do is I want to find out the pressure distribution in this fluid. So I know that the net force acting on any fluid volume I take, the net force acting will be 0. So using those ideas, I'll find out the pressure distribution in this fluid volume. And we'll discuss why this is important, but that's the only task that is required. You need to find out the pressure distribution so that if you immerse a solid body in this fluid, you'll be able to find out what forces are acting because of that pressure distribution in the fluid. So we have taken an imaginary fluid volume that I've denoted using this cube. Let's call it a cuboid, not a cube. So that means it has different sizes in different directions. So let me zoom into it. So the size is small. So I'll call delta x, delta y, and delta z. So this is my x direction, this is my y direction, and this is my z direction. And remember, this is the origin is somewhere outside. Okay, so this is the origin. So we are measure. So this cube is centered around a point P, which is at a distance. So this. So it has a position coordinate x. So x, y, z are the coordinates of point P. I mean, you have been doing these things, deriving relations using differentiation and integration. So we are doing nothing new, but stay with me so that you get used to these kind of derivation. And then if you understand these things, then you'll feel less pressurized when you see those complicated equations in front of you, because you know that how they are derived. Right. So what we also do is we say that since we've taken a collection of fluid particles making this cuboid, then now this is my free body. So then whatever's outside this cuboid of fluid is applying forces on this free body. So the water outside, the liquid outside this free body is applying a force. So this I'll call Fx, because this plane that we have here, this one is at a distance x from the origin. And similarly, the force acting by the liquid on the right hand side plane, this one, this is F at x plus delta x, because this plane is at a distance of delta x from the left plane. Similarly, you have forces Fy, and then I won't draw the Z1 because the figure becomes cluttered, but you can understand where the Z direction forces are acting. Just cleaning this figure a bit. Right. So now what we'll do is we'll use the idea that this force acting because of the liquid from the outside of this cuboid is because of pressure. And since we're talking about a very small cube, so we can assume that on the left-hand side plane, the x plane that we've talked about, where Fx is acting, there is no change in pressure along the y and z directions, because it's such a small area. So the force acting on the left plane, Fx, is the pressure acting on, I mean, at a distance of, at coordinate f, x, y, z, times the area. Now the area of that plane is delta y times delta z. Okay. And f of x plus delta x is this, but with a negative sign. I've taken the sign in because I've already given you directions. Well, in fact, then I should not be putting the sign, right? Because I've already drawn the direction. Is that clear? So now we can use Taylor series, and from there, I mean, what the Taylor series tells us, if you, I mean, just checking, you've learned about Taylor series in your mathematics course, right? Can somebody please confirm?
Yes, sir.
Good. So Taylor series, what it does is, if you know the value of a function at a point, let's say point P, you know the value of the function at P, and you also know the value of all the derivatives of the function at point P. Then you can calculate the value of the function at some other point in a neighborhood of point P. So all I know is the information about the function and all its derivatives at point P, and that helps me calculate the function value at any point in this neighborhood. And this neighborhood size is depends on um, the analytic nature of the function. Okay. So if the function is analytic everywhere, like e to the x kind of a function, then this the circle or a sphere is of infinite size. But for some functions, this has to be small. And in small neighborhoods, all the functions will show this analytic nature. So then, I mean, most of the nice functions will do that. So we can use this idea. Yes.
So could you please repeat this, like point P जो आपने अभी बताया?
Yeah. So this is a mathematical idea. I'll repeat that. So what this says is, if you know the value of a function and you know all the derivatives of a function at a point P, then you can calculate the value of the function at some other point, let's say Q, which is in a neighborhood of that point P. It's a very strong idea because you can calculate. I mean, all you need is you need to know the value of f df by dx, df by d2f by d2x, and I'm talking about 1D. So you know all the derivatives of the function and the function value at a point, and then you can calculate the function value at any point in its neighborhood. That is what Taylor series gives us.
Okay, sir.
So what we'll do is we'll assume that this point P that we have drawn here, okay, here, this is our point P. So I know the value of the function, that is the pressure function P, and let us say all its derivatives at point P. Then using that, I will calculate the value of P at x plus delta x comma yz using this. So what this Taylor series gives us, this is Pxyz plus del P by del x at point P. This is I call it point P times delta x plus del 2P by del x2 at point P times delta x squared plus dot dot dot. Okay. So this is what Taylor series gives us. So I was able to find the value of pressure at x plus delta x using the pressure at x plus all the derivatives of pressure at x. Right, and since we're talking about delta x is small, right? So what that means is, ultimately, remember, I would want to find out the difference. I would want to find out this value. Okay, so how does the pressure change if I go from the left wall to the right wall, from the left plane to the right plane? So that is this pressure, and this is equal to, in fact, I can say this is approximately equal to del P by del x at plane x times delta x. And all the higher order terms are neglected because if delta x is 0.01, then delta x squared is 0.0001. And if you add them, then if you add them 0.0101 is approximately equal to 0.0. So since you want to know this difference, then this difference can be nicely approximated by only the first term. So you have been doing this again in calculus. I'm just repeating those things. So what this gives us a delta f x. So net force acting on this is a free body, right? This water cuboid. So I want to find out the net force acting on this body in the x direction. So that's delta Fx. That is equal to, now I'll put a sign here because that's in the left hand side. So that's a minus sign with del p by del x times delta x, and then this is multiplied by the area, which was delta y times delta z. Okay, this volume of the cuboid I'll call delta omega. That's delta x, delta y, delta z. So this is, I'm sorry, this is a vector. So this is the force acting, the net force acting on this water cuboid in the x direction. Now, similarly, by the same idea, if I find out the net force acting on the cuboid, that will be minus del p by del x in I, minus del p by del y in j, minus del p by del z in k. All this multiplied by the volume of the cuboid. And from your vector calculus, that I'm sure all of you understand and very well now, you've done a course on electrodynamics, right? All of you.
No, sir.
Have you learned about vector calculus in any other
So
course?
it's going on in this.
It is going on. Okay, okay. Well, but are you aware of this gradient symbol and notation? Till now, any course has discussed that?
No, sir.
Okay. Well, in that case, that's a shame that not done any course. My life becomes difficult. But let us say this symbol, this upside down triangle, it's called the nabla symbol. This, when you put it in on the left hand side of a scalar, then that gives you this quantity del p by del x in I direction, del p by del y in j direction, and del p by del z in k direction. And you will again, if you are doing the course on continuum mechanics, then there also this will be discussed. But I mean, feel free to ask me about any question if you have regarding these things, but after the class. So for now, we can just say that this is a shorthand form of this expanded form. So if you apply the nabla symbol, the gradient symbol, it's also called the grad symbol or the gradient symbol. Because this basically tells you what is the change, the gradient in p with respect to x, y, and z in different directions. Okay, so there's a lot we can say about gradient operator, but we'll not do that right now in the interest of time. And so this is the net force acting, the net vector force acting on this, this imaginary fluid volume, delta omega. And since we're talking about a volume delta omega, so it's more, it's better to talk about the force per unit volume. That makes more sense. And this we see is equal to minus times the gradient of pressure. Okay, so this is denoted by F sometimes. It's called the force per unit volume. So that's the force per unit volume acting because of the pressure. So we can see that these terms, if your pressure changes in different directions, that will result in a net force acting on the volume. And this is exactly what we wanted to find out. We want to find out the force that is generated because of a spatial change or a spatial gradient in the scalar pressure field. right? So this is the idea. Out of all the mathematics I've done, this is the underlying idea. Spatial pressure distribution results in a force on a fluid or a solid element. So if the pressure was same everywhere, then there'll be no force. Or if the pressure was same in all y for all y values or for all z values, then there'll be no force in the y or the z direction. So since you are doing a course on electrodynamics, I'll give you a question that you can solve. So if these are my isobars, that is a constant pressure line. So let's say this is pressure P1, this is pressure P2, this is pressure P3, and pressure increases as you move out radially in this direction. So this can be a pressure distribution. In fact, we see this kind of a pressure distribution a lot in the atmosphere. So this is a pressure distribution because of some phenomena of winds or something. Then what will be the net force generated if I put in a solid body in its path? So what will you have to find out direction of grad P, and then from there find force on body. Also, it's a direction of force. So if I put a body here, then what will be the direction of force on this body? So these things, I mean, this is again question for you to try in your own time, think about it, and discuss with me later if you're confused about it. So we'll have tutorial session to discuss all these questions that you have accumulated in case you could not answer them, or you thought you will figure them out but you could not figure out. Okay. Right. So now that we have figured out what are the forces acting because of a given pressure field, let's actually try to calculate the pressure field for this for some situation that is known. So this is a situation of fluid statics. So fluid statics means that any fluid volume you take, the net force acting on that volume is going to be zero. So let us take, and this is on any fluid element. Okay. You could take it as big or as small as possible. It will be zero because the fluid is stationary. Now let's say that the blue liquid, the fluid volume that we had taken, considered earlier, that blue cube, this one. So for this one, since this is also stationary, right? So that means the net force acting on this volume has to be zero. But there is some force acting because of pressure distribution. So the fluid around this blue volume does have a net force because of pressure. So what we say is for the blue volume, or for the blue cuboid of fluid, let's apply this fluid statics equation. So what are the forces acting on it? One is the force because of pressure. I'll put a delta here. Everything is small. And in addition to that, there's also a gravity force. Okay. And actually, these two forces balance each other. The right hand side is also a zero vector. So we already know, we just now calculated that this pressure force acting on the body is simply minus the gradient of P times the infinitesimal volume delta omega. And then the gravity force is nothing but mg. The mass is density of the, in this case, everything is, even the blue volume is the same fluid. So I'll use only rho symbol for density times the volume, that's mass, times G. And just remember that this grad P, this actually is a vector. So I'm not putting a vector sign because it's a common notation that P is a scalar, but when you put a grad symbol behind it, this actually results in this quantity that I've written here. So this, by definition, becomes a vector. So we don't put an arrow like this over grad P because that's redundant. So you'll see some books doing that, but we will not do it. This is equal to 0 vector. So what we see from this is that grad P in this case is equal to rho times G.
So, what about the direction? Like gravitation force will act downward only, but in the that grad p is on the we are taking the gradient in the three axis. Then how it is like
Right, right.
balanced?
That's a good question you're thinking about. Give me a minute. I'll clarify that when I proceed from here. Because I haven't told you where exactly we are. I haven't told you we are on Earth. Right? We could be anywhere. So
Okay, sir.
we are developing a general relation. But as soon as I tell you we are on Earth where gravity direction is a specified value, then you can figure out the pressure distribution. But right now, we are writing things in a general way.
Okay, sir.
Okay. Right. So let's proceed from here. So let's say we're talking about liquid. So if we are dealing with, so I didn't tell you what the fluid we had. So if we have a liquid which is incompressible, so it could be water in a jar or something. So for that incompressible liquid, your density, incompressible means density is constant. So then I can write my grad P as rho times G, where rho is a constant now. And let's put the values for these as well. So grad P was del P by del X in I plus del P by del Y in J plus del P by del Z in K. And this is equal to a constant rho times minus G K hat. So gravity is always acting in the negative K direction. So that's what it is. So from this vector equation, we already know that these two are 0. So what this gives me is del P by del X is equal to del P by del Y is equal to 0. So that means my pressure cannot be a function of X and Y, because if it was a function of X and Y, then I will not get this 0. So that means, so this implies that pressure is only a function of Z. And we are getting something we already know. I mean, pressure only varies with height, but let's do that mathematically. So pressure is only a function of Z, that we get from this relation. So I can, so if pressure is only a function of Z, then instead of writing partial P by partial Z, I can write dP by dZ, because P is pressure is a pure function of Z now. It's no X and Y. So this becomes equal to, from this relation, minus rho G. Okay, so let's integrate that. So let's say this is my P1, this is my P2, and this is at height Z1, this is at height Z2. And remember, rho and G both are constants. So this gives me P2 minus P1 is equal to minus rho G times Z2 minus Z1. Okay. And this basically gives us, I'll write P1 is equal to P2 plus rho G times delta Z. Z2 is greater than Z1. That's higher. So we take a reference, let's say from here. And this is the relation of hydrostatics. P1 is equal to P2 plus rho g delta z. So you'll be a bit annoyed that we've done all this just to get whatever we already know. But the reason we did this is because now I'll solve a couple of problems with you where we can calculate pressure fields for non-usual situations where things are rotating, situations where things are accelerating, frames which are if you have water in a jar which is in a car that is accelerating. And these ideas were somehow known to us, but we are again formally doing that in this lecture. Any question? Now let's go back to that relation where we had grad P was equal to rho times G. Now there is something we know, and that thing, if you when you study vector calculus, you learn is that the gradient of any scalar function is, this is a vector, right? So this grad P is a vector. So this vector is perpendicular to the constant P lines. So this I won't do. I mean, you can do it mathematically, and you will probably learn that as a part of electrodynamics course. In case you do not, then let me know. Then we'll do it in some extra class. All these mathematical ideas, but you need to know as an engineer, as a mechanical engineer, you will need to know how this is done at least once. You need to see the derivation. But this is something that for right now, let's say we knew the mathematics and we have learned that the gradient of a scalar field is perpendicular to constant field lines. So what that means is, I mean, for remember that example question I gave you, circular things. So I've answered that question anyways. That your pressure lines, constant pressure lines here are circular. The isobars are circular. So that would mean that grad P is perpendicular to that. So grad P actually would be in this direction. So this is something that is known mathematics. There's no physics here. Okay. And this relation, this one that I have put an arrow on, this tells us that this grad P will always be in the direction of gravity. So what that tells us is that the variation of pressure now, because let's say on Earth, if you're talking about the standard frames we work with, gravity is like this. So grad P will also be in this direction. So what that means is the constant pressure lines will be perpendicular to this vector. So these are the constant pressure lines. Now again, that is something that we just figured out from here. And as you go up, as your Z increases, then your pressure will reduce. Okay, so I mean, I'm doing these things very slowly with you, so you can see that we are developing intuition from the equations as well, rather than solving the complete equation. Later, only seeing this relation will help you interpret these ideas, but they come with time. I mean, you'll have to give yourself some time, a few years, until these things become very natural for you. Any questions? Now, this was for liquid. So we started with incompressible liquid. Now, let's talk about gases in the atmosphere. So for gases which are compressible, let's try to solve this equation to get the pressure field. So if our blue cuboid was actually in a gas, we had a stationary gas. So in that case, your density is not a constant. Density will change. So you will need some sort of relation between density and pressure. Otherwise, you cannot solve this equation. And that relation, you may already have guessed, will come from the ideal gas law or real gas law, whatever it is. Okay, so I can write for my ideal gas law, I can write my density in terms of pressure as P by RT. Okay, R is contains the information about the universal gas constant and also about the molecular mass of the gas. It's a constant for a given gas. Okay, so now we can solve this again. When since we're talking about Earth's gravity and so on, so this again gives us dP by dz is equal to um, minus P by RT times G. And then when we solve this, well, you can do it. You can solve it, solve this differential equation, and that gives you, after the few steps, P2 is P1 times e to the power of minus G by RT times delta Z. So again, we see that as we go up, as our Z increases, so this is Z1, this is Z2. So for Z is equal to 0, that is delta Z, basically at this point where Z is 0, your delta Z is 0 here. So you get P2 equal to P1. So that's this basically is P1 is your pressure at Z equal to 0. And as you go up, you will see that the pressure reduces because you have a negative sign. So it's an exponentially decaying pressure field that you get with height. And that is what you will see in the atmosphere. Okay. But that will only be true for small ranges of height. The reason being that temperature is not constant in the atmosphere. Right now, we have assumed that temperature has no relation with pressure here, but that is not the case, right? So it's all about approximations. Under what approximation are these things valid? So if temperature, this is true for small changes in height. So we're talking about let's say 100 meters or so, then it's okay. It's okay to assume that temperature is constant. But if the temperature, I mean, if you're talking about scales of kilometers, then uh, you'll need some sort of dependence of temperature with height. So in atmosphere, what we do is we use a linear approximation that temperature reduces as you go up in troposphere. You know that, and then you can fit the temperature change as a linear curve, and C is a constant you can calculate from your fitting. So you will find in handbooks and so on, these relations are given. So if you do that, if you substitute this relation, because if you wanted to solve this differential equation for a larger change of heights, then you can do that. So I'll leave it as an exercise to find P as a function of Z for changing temperature. And changing temperature like this, where C is a known constant. This will help you exercise your differential equations a bit further. Okay. Now T naught is the temperature at Z equal to 0. That's a sea level temperature. Any questions? You've done a lot. I want to stop now. So we can use the next couple of minutes for questions. So let me ask you a question. It could be homework for you to think about. Let's not use homework. Sounds very schoolish. Exercise. So using the idea that I just talked about, that grad P is equal to rho G, using the equation that we discussed, show qualitatively through a discussion that when if we have a vessel that has some water in it, if I tilt the vessel, then even after tilting, what I see is that the water is horizontal. So using this equation, can you argue that the water level will remain perpendicular to gravity even if I tilt the vessel? Is my question clear? You can think about it later. I mean, if you want, it's okay. But do think about these things. Great. So we'll stop now and we'll continue from here tomorrow. So we'll need probably one or maybe half a lecture on fluid statics. I'll stop recording the lecture and you can ask questions if you like.